Okay, we are now going to change gears in this class and start to introduce uncertainty into our models. Up until this point, there has been no uncertainty. Every single model was fully deterministic. Sometimes these are referred to as perfect foresight models in the sense that the planner can choose an optimal solution to implement at date zero and just carry through that plan forever and know with certainty what's going to happen because there's never any randomness to the outcomes. So we want to modify that. Obviously, modern macroeconomics, if you want to talk about business cycles or even growth, we need to incorporate some type of uncertainty into the model. Okay, and so this is going to be our first kind of foray into that. If you guys, everybody but Nathan, Nathan, I don't know if you're going to take the second semester macro PhD class, but for the rest of you guys, in Sarush's second semester macro PhD class, pretty much all of the models are going to have some form of uncertainty in them. Business cycle models, asset pricing models, new Keynesian type models. So here we're going to start to talk about how we incorporate them into this growth context and how we can use recursive techniques, that is dynamic programming, to deal with or accommodate uncertainty. Okay. All right. We are going to focus today on economies in which the stochastic variable, the variable that is random, can only take on finitely many values. Okay, so we're not going to be looking at a model that has what's known as a continuous random variable. Okay, so this is going to be somewhat of a simplification, but in the end, it's not going to change our main results. The reason I'm going to do this is because it prevents us from having to use concepts from measure theory directly to analyze the solution to the model. Okay, some of you may have had measure theory, some of you may not have been exposed to it at all. I don't want to have to wade into those waters, and so what I'm going to do is just use stochastic variables that take on finitely many values. Now we can get close to a continuous random variable by simply assuming that the random variable has capital N different possible values that it can be, where N is a really large number. All right. But in a lot of practical applications, you can think of this as good shock, bad shock. And over time, you either get hit with the good realization of the shock or the bad realization. Okay. This restriction enables us to use Markov chains as a way to describe the stochastic process, which I'll define in a minute. Again, some of you may have seen this concept before. I'll define it more formally below. What is the goal? The goal is not for you to be experts on the various proofs of stochastic dynamic programming. Okay, the goal is for you guys to understand the tools of stochastic dynamic programming so that you can apply them in practice. All right, I want you guys to have a working knowledge of how to set these problems up and characterize their solutions, albeit problems that have randomness to them. Okay. Have you guys gotten to expected utility theory yet in micro? No? You haven't done any of that yet? Okay. Have you done consumer theory? What are you doing in micro right now?
So we started on applications to the consumer theory.
Okay. But you haven't talked about uncertainty yet in micro. So not expected utility theory. Okay. All right. Let's think about how we can incorporate expectations into dynamic programming, because we're going to need to do this. If there is randomness in these models, then the planner or the representative household is not so much going to be maximizing utility as she's going to be maximizing expected utility, where the expected utility is going to be weighted by the various probabilities of these different stochastic events occurring. Okay. All right. We're going to define the variable ZT as our stochastic random variable that takes on finitely many values. So zt, little zt, is going to be an element of big Z, where big Z is just some set of possible z's. Let's call it z1, z2, all the way to some zn, where these are written in ascending order, right? So z1 is less than z2 is less than zn, and n is finite. Okay, that's important. The fact that the set Z has finite many different values means that the set Z is compact. That was an important assumption in our dynamic programming applications. The state variable in our problems, sequence problems, had to live on a compact set. Okay, well, the random variable is now going to augment the state vector in these types of models. And so it needs to also to live on a compact set. All right, so the fact that n is finite means that Z lives on a compact set simply by assumption. Right, so Z, shake your head yes if you understand what I'm saying here. Z is a random variable, and in any given period, it can take on any one of these different possible values. We don't know ahead of time what it's going to be. It could be a low one, it could be a high one. But any given period, we're going to take a draw from this distribution here. Well, this is not a distribution. This is the support of the distribution. All right. Okay, what does the utility function look like now? Well, and again, I'm going to talk about the generic problem here. So this is not the growth model per se. The instantaneous utility function will now depend on three quantities. It will depend on the state xt, right, where xt is an element of some set x, which is a compact subset of k-dimensional Euclidean space. Xt plus 1 is the control, and zt lives on this set z, is the random variable, right? So now there are three elements that define the utility function, not just the state and control, but also the random variable. In fact, z is now going to be part of the so-called state, which I'll get more into today. Okay, so the utility function then is going to map elements of x product z into the reals. Beta is again going to be defined as the subjective discount factor in these problems. And not only is the initial value of the state going to be given, but the initial draw of the random variable z will be given. So at the beginning of time, the planner sees what x0 is, as well as what the initial draw of the random variable is. What the planner doesn't know is what z1 is going to be, or z2 on out to z infinity. She has to make her decision based on an expectation of what those z's are going to be. So we'll assume that the planner knows the distribution that the z's are drawn from.
So that initial z, that's an expected z.
No, it's one of these particular z's, right? So I'll get more into this later today, but the realization of the shock occurs at the very beginning of every single period. Okay, and so the planner or the decision maker sees what the value of that shock is for this period, and she makes her consumption and investment decisions based on that observation. But in doing so, she has to think about what z is going to be in the next period, because that has an effect on lifetime utility, right?
So this is something that's already observable. This isn't like something that
yeah, no, the z's are observable. They're just not known ex ante. We know what the z's could possibly be, right? For instance, when you flip a coin, Ben, you know that it's either going to land heads or tails, but you don't know every period what the event is actually going to be. But you do know.
Z0 is like a head.
Yes, yeah. So it's like you flip a coin at the beginning of date 0, it's heads. Okay, you know that information, and then you have to make decisions based on the likelihood that z is going to be heads or tails in the future.
So this isn't like a process that hasn't happened yet. Like Already in progress.
It's already in progress, that's right. And the planner knows the probability distribution. So she understands what that stochastic process is. Okay. The constraint correspondence in the problem is also going to be a function of the random variable. So this set valued mapping G, which in the deterministic world told us all the possible values for xt plus 1, now also depends on the shock itself. So at the beginning of period t, once the shock is realized, that's going to determine in part, in concert with xt, what all the possible values of xt plus 1 could be. Right? So G then is now the set valued mapping that maps elements of X product big Z into the space of X. It shows us all the feasible possible choices for xt plus 1, that is our control variable. All right, let's talk a bit more about Z, in particular, the process that governs the evolution of Z. In this class of models, we're going to assume that uncertainty can be described using a first order Markov chain. So ZT is going to follow a first order Markov chain. Now, what does that mean? Well, there's a formal definition in your lecture notes, but a stochastic process Z from t is equal to -infinity to infinity has the first order Markov property if and only if, for all t and all possible values of j between 1 and capital N, we can write the probability that ZT is equal to some ZJ conditional on the full history of Z's up through period t minus 1 as being equal to the probability that ZT is equal to ZJ conditional on only knowledge of ZT minus 1. Now let's stop here and think about what this says. You've observed the history of Z's all the way up through period t minus 1, okay? And what you want to do is determine what the conditional probability then that ZT is equal to ZJ in period t. The stochastic process for Z exhibits a first order Markov chain, or follows a first order Markov chain, if that conditional probability doesn't depend on any of the Z's from Z0 through ZT minus 2, but can be determined simply by observing what last period's shock was. In other words, all the information you need to determine the conditional distribution of ZT is contained in what the value of the shock was in the last period. If that is true, then Z takes on this first order Markov property. This type of process is useful in economic models in which the stochastic shocks in the economy are correlated over time. For instance, for those of you who know something about time series econometrics, a lot of macroeconomic shocks take on a first order autoregressive form, meaning that if there's something that causes GDP to be higher today, a stochastic shock, it tends to mean revert slowly over time, right? So that it doesn't immediately fall back to its mean value, but rather if you observe a positive shock today, you're going to tend to see positive shocks tomorrow and the next day, etc. So shocks that tend to be correlated over time instead of shocks that are purely white noise can be modeled easily in a macroeconomic context using this first order Markov process. Now, the Markov property also allows us to utilize a pretty simple notation to describe the probability distribution of the shocks, Z. Specifically, it allows us to make use of this thing called the transition matrix, which I'm going to label capital Q. Now, what does the transmission matrix tell us? Each element of the transition matrix tells us the probability of transitioning from one state in period t minus 1 to a different state in period t. So for instance, let's say that the transmission matrix has the following general form: Q11, Q12, all the way to Q1 capital N, Q21, Q22, all the way to Q2 comma N, QN1, QN2, all the way to QN comma N. This is an N by N transition matrix where each element of the matrix, again, shows the probability of transitioning from state I to state J. So for instance, the probability that ZT is equal to ZJ conditional on ZT minus 1 being equal to ZI can simply be written as little q I comma j, right? So the probability of going from state I to state j is given by the ijth element of the transition matrix. So what the transmission matrix shows us is effectively the full conditional probability distribution of the stochastic variables in this model. All right, think about it. This is assumption 1. What must the sum from j is equal to 1 to cap n of qij be equal to? So let's take the ith row of the transition matrix. What must the sum of all the probabilities in the ith row equal? That's the probability of moving from state I to state j, summed over every possible state j from 1 to cap n. That probability must equal 1, right? So each and every row of the transition matrix basically summarizes the conditional distribution of ZT. That is, if we know what the state is in time t minus 1, the particular row of the transmission matrix tells us what the probability of transitioning to each possible future state is going to be. This is how we're going to model uncertainty in the optimal growth model. The planner, standing at time 0, does not know what particular path of shocks are going to emerge over time. Just like if you stood today and had a fair coin and you flipped it 10 times, you don't know whether you're going to get heads, tails, or heads, tails, right? There's a bunch of different possible paths that the random variable can take. But what the planner does know is all of the possible paths that it could take, as well as the likelihood of each of those paths occurring. That is, she knows the full distribution of the random variable z and takes that information about the distribution of z into account when making optimal lifetime consumption and savings decisions. Okay, let me, in the rest of the time that I have today, let me start to try to illustrate some of these ideas by going ahead and discussing what the stochastic optimal growth model looks like. Again, I'm not going to characterize the solution to this model yet. That is the Brock-Merman model, until we get to the next section. But what I want to do is just set up what the problem looks like so that you guys understand the new concepts that are added to this type of economic environment, okay? All right, what does the objective function look like now for a benevolent planner in the optimal stochastic growth model? Instead of maximizing discounted lifetime utility, what the planner has to do is she has to maximize the expected value of this objective. So this capital E denotes an expectations operator. You guys familiar with what that is? An expectations operator? Surely you've seen this in math camp or in stats class before, how to evaluate an expectations operator, right? If you know what the probability density function is, you can take the integral of the random variable times the PDF, evaluate it over the domain of the random variable itself, right? Okay. What does the little 0 mean in the subscript? That is the, this denotes it's a conditional expectations operator, meaning that it's, so E little 0 is basically the following. It's the expectation of some object conditional on information at date 0. It's basically what it means. So the planner observes X0 and Z0 and makes an expectation of what lifetime utility is going to be based on that observation. Again, she doesn't know what Z's are actually going to occur, but she does know all the possible different Z's that could occur. And she has to form an expectation over those future realizations based on the likelihood that the Z's will occur, because she knows what the probability distribution function is. The production function in the optimal growth model looks similar as well. Yt is equal to f of kt, but now the production function is hit by these shocks zt, okay? So y is output per capita, kt is capital per worker. Zt now has a clear interpretation, all right? In the optimal growth model, the source of uncertainty are these shocks to the production function, which means that for a given amount of physical inputs here, if Z changes, that changes the amount of output that can be produced from a given amount of capital. So we interpret Z's as stochastic productivity shocks or stochastic technology shocks. So that's the way uncertainty is going to enter into the optimal growth model. Obviously, there are other ways that uncertainty can enter into those models as well. But in the basic optimal growth model, we're going to be talking about technology shocks. What does the resource constraint look like? Well, capital stock at date t plus 1 is simply going to equal how much is produced today plus whatever capital stock is left over after depreciation from the previous period minus how much we decide to consume, where of course kt is bigger than or equal to 0. Now this is important because this setup here, this formulation of the resource constraint implies that at the time the planner is choosing consumption at date t, the value of the shock has already been observed. So just like Z0 is observed before the planner makes decisions about consumption and savings, if we think of this as period by period, then the realization of the shock occurs at the very beginning of date t. That determines how much output is produced, along with the amount of capital that's determined or carried over from the previous period. And therefore, consumption, what we optimally choose or endogenously choose to consume today, will depend on the shock ZT. So we observe, or the planner observes the technology shock before making consumption decisions in period T. Now, ZT itself depends on ZT minus 1, because we're talking about a shock that has the first order Markov property. And ZT minus 1 depends on ZT minus 2. ZT minus 2 depends on ZT minus 3, etc. What does that imply then about CT? CT does not just depend on what happens today, but rather optimal consumption at date T depends on the entire history of shocks from period 0 all the way up through period T. This is an important point that you got to understand about these stochastic models, is that the endogenous variables, consumption and investment, or the capital stock for next period, don't just depend on today's technology shock. They depend on the entire sequence of technology shocks up to that particular point. Now, to state that more formally, we need to define a little bit of notation here. Let me define Z superscript T as being the following. It is a vector that contains the realization of Z all the way up through and including period T. Now, I'm not going to include Z0 in this vector. It's understood to be known at the beginning of time, but also I'm going to do it out of convenience, because that means that this object is little t dimensional, okay? I'm going to define big Z superscript T then as the following T times product of all the big Z's. Where T is countably infinite over time. Okay. What I'm trying to say here then is that if consumption depends on the entire history of shocks up through and including period T, then whatever the optimal value of consumption is at date T, we can think about it in terms of what's called a state contingent plan for consumption. Now, I'm going to develop some notation here that I'm warning you is a little cumbersome, but then once we start to analyze these problems recursively with a Bellman equation, all of this notation goes away. But I want to introduce it now so that you guys conceptually understand how the planner is actually solving these problems with uncertainty in them. I'm going to denote this notation C tilde of Z superscript T in squared brackets. This is not so much a specific value of consumption as it is a function that shows us what consumption is going to be equal to today, given the entire history of shocks starting back in date 1 or date 0 all the way through date T, right? Depending, that path of shocks could play out very differently, which will cause consumption to be different in period T. So that's why I want to denote this as instead of a particular value of C, think of this as a state contingent function or plan for CT. Okay, if CT depends on the entire history of shocks leading up through period T, then if we go back to the resource constraint, we say that KT plus 1 is f of KT ZT plus 1 minus delta KT minus C tilde of Z superscript T. What that implies then is another major point that I want to emphasize here, is that the optimal choice of capital at date T plus 1 is going to depend on what? Not just the current value of Z, it's going to depend on the entire history of Z's up through and including that point, which means that we can think of KT plus 1 as also being some contingency plan, let's call it K tilde of Z superscript T. Now you'll notice that KT plus 1 does not depend on ZT plus 1. Please be careful about that. When the planner at date T is choosing consumption, she's also choosing what KT plus 1 is going to be. But she doesn't know what the actual value of ZT plus 1 is going to be until the beginning of the next period. However, KT plus 1 is predetermined in period T. So the planner's consumption decision in period T therefore determines what the capital stock is going to be in period T plus 1. So KT plus 1 is not a function of ZT plus 1. It's a function of ZT and everything that preceded it. Okay, does that make sense so far? All right, if I were to adopt this notation, then what would the sequence problem look like for the planner in this world? Remember, in the optimal growth model, the planner is going to maximize over sequences of capital and consumption. But instead of maximizing over a specific sequence of capital and consumption, in a stochastic world, the planner has to maximize over sequences of state contingent plans for capital and consumption, where she has to take into account all the possible different trajectories or paths that Z can take over time. And she chooses that to maximize the conditional expectation of lifetime utility, beta to the T, U of CT. Now what is, let's be careful here, what is CT equal to? Well, let me just write it as CT first, just so there's no confusion. Subject to a period by period resource constraint. Now, what is that resource constraint? It's KT plus 1, which is the same as K tilde ZT, is equal to F of K subscript T, which is K tilde ZT minus 1, because KT is determined by the shocks up through period T minus 1, comma Z sub T, plus 1 minus delta K tilde Z superscript T minus 1 minus C tilde Z superscript T, where C tilde of ZT has to be greater than or equal to 0, and K tilde of ZT has to be greater than or equal to 0, where initial capital, of course, is given. Okay, let me try to explain this problem in a little bit simpler of a case. Imagine for a moment that the technology shock could only take on one of two possible values, okay? Either, let's say, a good value G or a bad value B. There's only only two possible values here, okay? So in period T is equal to 1, ZT is either going to be G or B, okay? Now, in period T is equal to 2, what could happen? Well, if the shock was good in period 1, then in period 2, the shock could be either good or bad, right? However, if the shock was bad in period 1, in period 2, again, the shock could be either good or bad, correct? What about period 3? Well, if this was the path we took, G, G, then we have two possibilities, either G or B. If instead we went G, B, then again we have two possibilities, G or B. We have two possibilities for every one of these, every one of the four possibilities in period T is equal to 2, right? And we know what Z0 is. It's either G or B, one or the other. So if we just analyze this problem with two possible states of the shock for 3 periods, how many different possible paths can the shock take? 1, 2, 3, 4, 5, 6, 7, 8, right? Easy. For 3 periods, there's basically 8 different ways in which the shocks could roll out over time, given some known value of the shock in period 0. Essentially, what the planner is doing here in this problem, imagine there's just 3 periods and only 2 possible values of the shock, is the planner is thinking about at date 0, all of the possible paths that the shock is going to take place over time. And the planner also knows what the probability that each of these paths are going to be. Why? Because the planner knows what the distribution of the Z's are, right? So you know what the probability of flipping 3 heads in a row is. You know the probability of flipping 2 heads and then tails. You know what the probability of flipping a head, tail, and then head, etc., right? So you can evaluate all of those different possible paths over time, as well as the likelihood of each path playing out. What the planner has to do then is she has to think about, okay, let's assume that this was the path that the shocks are going to take. What is the optimal sequence of consumption and capital given that particular path? Okay, what if this path plays out? What's the optimal sequence of consumption and capital in that world? That's what the planner is doing here, is she's effectively solving a bunch of different perfect foresight models and putting those all together in this state contingent plan or sequence of state contingent plans over time. What K tilde and C tilde refer to, it shows us what the optimal value of consumption or capital is going to be in every period, given a particular realization of the shocks up to that point. And the planner has to think about all of the different possibilities as well as the probability of each of them occurring so as to maximize expected utility over time. So instead of solving one perfect foresight problem, the planner here is solving 8 different perfect foresight problems and attaching a particular probability to each of those different 8 events, and therefore determining what the sequence of contingency plans is going to be. Now imagine doing that in a world where there are capital N different realizations of the shocks and time goes on to infinity. This little decision pyramid here becomes immense, right? But that's effectively what the planner is doing here. Okay, is not so much determining the optimal values of consumption and capital over time, like in the perfect foresight deterministic model, but rather determining the optimal sequence of contingency plans. And I say contingency plans because consumption and the capital stock are contingent upon, they depend upon a particular realization of the technology shocks. Now, let me stop there. And here's where I'm going to pick up in the next class. This notation is very, very cumbersome, okay? It would be extremely annoying to have to carry around all of this notation all the time that indicates all of these endogenous variables are state contingent plans. Fortunately, however, this class of models has a recursive form, right? meaning that the optimal way that the planner chooses consumption today as a function of what the capital stock is today and the realization of the technology shock is today looks exactly like the optimal way that she determines that in the last period. So that instead of writing this as a sequence problem over an infinite sequence of state contingent plans, we can write this as a functional equation by setting up the appropriate Bellman equation and solving for the optimal policy function, which shows how the optimal value of kt plus 1 is determined by kt and whatever zt is. And that time invariant policy function takes into account or will accommodate any of the possible paths of the technology shock over time. So there is a recursive formulation to this problem. What I want to do is illustrate that recursive formulation. And then the main thing we want to do is is going to kind of mirror our discussion of the dynamic programming theorems from earlier in the semester, where we set up the sequence problem and then the functional equation. And we went through those various assumptions and theorems that established equivalency between those two problems. Okay. Now, fortunately, most of those assumptions and theorems are very similar, and so we can go through them pretty quickly. There are a few that need to be modified to some extent to account for the fact that we've got a stochastic variable in the problem. And there's one new assumption that we need to make regarding the monotonicity of the utility function with respect to z. And that's going to have implications on the monotonicity of the value function with respect to the state of technology, which will be important when we determine certain properties of the Brock-Merman model later on. So that's what we want to do in the next class, is kind of walk through those various assumptions that are needed to establish the stochastic dynamic programming theorems. What will it culminate in? Something that looks like, I believe, theorem 8 or 7 earlier on, which is, what is it that characterizes the solution to dynamic programming problems? An intertemporal Euler equation and a transversality condition. What we want to do is derive the stochastic version of the Euler equations and the stochastic version of the transversality condition. That way you can apply the dynamic programming theorems to these growth models later on. I'm going to try to get through all of that in the next class, but it may bleed over a little bit into next week, okay? But it's mostly going to be conceptual. There's not really going to be any proofs. We're going to be going over the assumptions and talking about the theorems and just trying to interpret what they're saying, okay? And then after that, we'll solve and characterize the optimal growth model, okay? In the stochastic growth model, that is.